Okay, so here I'm gonna continue with the video I was making earlier about how to model how to make the finite element model of a fracture fixation implant with the bone. So fracture fixation construct, I'm calling it here. Okay, so I was at the step where you define the materials. You have to make two materials: the bone material and the implant material, because I'm making them homogeneous and making the whole implant of the same material everywhere. Okay, so the material for the bone, I'm only gonna make it the cortical bone. It's linearly elastic, as I said earlier. It's gonna be isotropic, which means I only define one Young's modulus and one Poisson ratio, because I assume that the Young's modulus, the stiffness, is the same, so that the ratio of stress and strain is the same in every one of the three orthogonal directions. And then I'm gonna make it 15 gigapascals, which I'm putting it here as 15,000 megapascals, because I want the units of this to be megapascals. The Poisson ratio doesn't matter, the units is ratio, so it's 0.3. This is something, if you go on the internet, you'll find different values depending on what type of bone, if it's diseased bone, if it's this or that. But a sort of average I've found in some papers is 15 gigapascals, right? So 15,000 megapascals. Okay, so let's stick with that. Now, this second material I want to make is material for the implant. Actually, let's go with it. It's titanium, right? Titanium. Right, so it's also linearly elastic, the same as the other one, also isotropic. And for that, I found that 110 gigapascals is generally accepted value. So 110,000 megapascals. Now, and the Poisson ratio is also 0.3. Okay. Now you have to create a section of that material in order to assign that section to the part that you want to assign it to. I'm going to call it the same so that we don't have any. I'm just going to call it bone. Confusions there, right? And the second section is going to be the implant, right? Which is made of titanium. And then I go to my bone part. There's a part here that's called section assignment. I find it easier if you do it all on the tree. You can also go to these little icons here, but I prefer just doing everything in the tree. So you double click on the section assignments, and then you click on your bone. You have different parts of the bone. If you're modeling a fracture, then you have to click the different parts. Okay, so I just go here, and it asks me which section, and of course this is the bone. Okay, then I wanna also assign a section for the implant. Oh, right, I forgot something very important. Let's see if this works like this, but anyway, so as you probably noticed, I didn't model it with any holes or the plate with any screws. That's actually because I've done that before. At the beginning, I was tying the plate to the bone as suggested by my supervisor. Since he believed the stress distribution is not that different, and he was right. There are these big stresses at the edges of the plate, which is actually big focus of my thesis, master thesis. So anyway, that's probably why I forgot it, but I moved on after a while to do it with holes and with screws, because even though the general trend is similar, it's still much more accurate. So, and I realized it's also the speed is similar. So anyway, I'm gonna go back here, and what I'm gonna do is I'm gonna create an extra feature by going back to you, back to part. There's an icon here that says create cut extrude. So I'm gonna do it with you, and I select the plane for the extrude cut. So that's what I forgot. I have to make a plane first, which is going to be an offset from the, as you can see here, the X set plane, the plane defined by these two orthogonal directions. So the X set plane, and for now I'm going to make it 0. Actually, I should make it in 1 because it's going to extrude in one direction. So I'm going to make it 17.5, right, since that's the thickness of the bone. And then you go here. By the way, you can always click on view parallel to have a nicer parallel view. Okay, so now what I want is to make this extruded cut. I asked me for select a plane for extruded cut. I want to select that one. Select an edge or axis that will appear. Well, I can select this, is fine. Doesn't really matter. Now I'm gonna make the holes. For that, I'm gonna make these two construction lines. Construction lines are always useful, so you can define all the dimensions relative to them. And you should always, in Abaqus at least, you should always fix them, because otherwise they start moving around. So you want everything else to move around relative to these two construction lines that define like sort of axis, you know, from the middle of the play of the bone here. Okay, so I'm gonna make a few holes, and the way I decided to do it was to make the holes 4 holes on either side of the bone, and I want them to be I want them to be 15 millimeters spaced apart, but first of all, I want them to be you should be, what was it? I think it was something like 2 millimeters radius. No, that's a little bit too little. Let's make you, I think it was maybe 4 millimeters radius. That seems more reasonable. Yeah, okay, let's go with that. Might have been a bit smaller. I mean, for now, since an important thing to do is to always check how these things affect the rest, the results. Well, unless you're trying to model something that somebody has already discovered the effect it has, and then in that case you want to model this, you want to set this dimension exactly to what they set it. Otherwise, you can set it to whatever you want. Later, you can change it. That's the idea, right? Okay. So I'm gonna set a dimension also from this line, and I want it to be 15 millimeters, right? Is that correct? Yeah. Okay, and then you can, I'm sure, in SolidWorks, what I usually do is I make a pattern. I'm gonna look a little bit for a pattern. If I don't find it, what I'm gonna do is I'm just gonna make them. Select the type of translation operation, copy, and select the entity to translate. I'm gonna select you, pick starting position, and select the middle of the circle, pick end position. I'm just gonna select you, see what happens. See, but that's not something I want to do because, I mean, that's okay, actually, that's okay. And then I'm gonna also select starting position, select end position, no, select start position, select end position, okay. You know what, I'm just gonna go, I'm sure you can figure out how to do that, but no. Okay, so for now I'm just gonna go through all the lines. You can see that would make a nice hole through everything, but I actually want to have 4 holes on each side, so I'm gonna delete that Now the modeling tools of my excuse here is that the modeling tools of Abaqus are horrible. This is not a lie. I'm actually gonna model each of these damn holes. Da, da, and da, right? What I will do to make it a little bit smarter is I'm gonna, ooh, wait, no. Give these a dimension, give these a dimension, give these a dimension, right? But I'm gonna, you can do here is you can make these sort of formulas, and if I did this before, I'm gonna try and figure it out again. Current value, oh wait, you have to go here. No, you have to make it a reference, right? No, you don't. No, you don't. You cancel this here, and I'm gonna make, say here, this is gonna be D, right? For the, actually R, because it's the radius. It's handy if you can make a variable for the radius, because then if I want to change the radius later, which I do, then I can just change one of them and they all change, right? So that's something I really want to do. Oh yeah, so yeah, I'm gonna call this R. Yeah, so I just called the name of the damn thing R. All right, and then when I go on this one, I just say I want this to be a reference, and it's gonna be R reference, right? And this to be R, right? Exactly. So as you see, that changed to 4 now, because as I mentioned this. And again, this one I want to do the same. I'm going to call it R. And that's going to become 4 as well. And now for this, okay. And the same for this one, right? I'm going to call you R. Okay, now the next thing I want to define is their distances to one another. I want them all to be 15, right? So for now, I'm going to just call these. So first, you have to define some sort of dimension that you want to edit later. I want them all to be 15. So what I'll do now is I'm gonna go and edit each of them as I did before. Wait a second. Okay. I'm gonna go to this one first. I don't know, it doesn't appear here, but it should. I'm gonna call these the gap, right? It's the gap between them. And it's 15, right? And so I'm gonna call you again gap. Probably just one letter faster. And I go on you as well, and I go gap as well. So as you can see here very nicely, it's all dependent on only two variables at the end, which is very nice for when you want to modify later things. Seems like a lot of work right now, but it's going to save a lot of work later on. Now I'm curious why that's okay, this is the bone, right, by the way. So the reason I did it 15 is because these all adds up to 60, right? And if you go 15 more, it's 75, which is half the implant. So that's sort of nicely distributed into the space. Okay, so that should be it. Right? Oh, so the last step. I did not want to have to model that on the other side. So I'm gonna mirror them. So select type of mirror operation. I want to copy, select the mirror line. Of course, it's this one. Select the entities to mirror. Ta. By the way, use shift when you want to do control operations here to select multiple things. Not control, shift. Well, sometimes in other things like in the tree, you want to do control, but in the sketches, use shift. I didn't figure it out at first and drove me crazy. Okay, so that's all mirror now. And let's hope that when I click done, yeah, so every time you have to always regenerate. As you can see nicely, that's all the screws now. They're actually quite large. I did think about that at the beginning. But you see, now I actually realize this is too large. So what am I gonna do? I'm just gonna change this one to 2.5. I actually want all of them to be 5 millimeters diameter. And look, all of them changed instantly. So that's very nice. And I regenerate that, and they're a bit smaller. They're 5 millimeter diameter each. But of course, I gotta go with the same thing in the implant. I'm sure there is some faster way to do this as well, but I don't know how. So now I'm gonna go into my implant, see if I can import something. Nah, I don't know. Import. No, I can't import. Options maybe. Anyway, I'm just gonna create another plane. Again, in the XZ plane, so I offset it from the XZ plane of 17.5 such that it is, actually I don't want that to be like that. By the way, you can always go, and so right now I realized that's not really the dimension I want, so I'm gonna actually want it to be over the top surface of the plate, which, as you remember, was a 21 point. I want it to be a little higher. I want it to be at 22.5 such that it's 1 millimeter. It looks a bit more like real screws, right? It's 1 millimeter above the I also want some color view here, above the top surface of the implant, the plate. And now I'm gonna go and make some extrude. Before I did a cut, now I want to just make these parts, right? Extrude a few circles that are gonna be my screws. So it asks me for select a plane for extrusion. Select the edge that will appear. Select this one. Okay, so I go and do my usual thing. Make these two construction lines. Then I make them fixed. Then I'm just gonna stop talking a bit because I've already done this before. So, just go back to the other part if you want to know exactly how I figured out all these steps. The one thing this one is nice for is if you want to skip all the trial and error that I did before, you just look at this one, because since I did it before, I guess I'm a little bit faster. Anyway, so I go and I click on you, and I'm gonna call you again. This time I call you G, and you. By the way, if you want to move things around, you always use this little thing in SolidWorks. You can actually move it right away. Anyway, so I go on this one, and I want to call you R, right? Yeah. So I call you, I'm going to make you the same as R, apply, make you the same as R as well. Make you the same as R. Okay, make you the same as G. Make you the same as G as well. I'm gonna make you same as G. That should be it. Now, the final stage, I mirror all these. I pick copy, pick the mirror line, select the entities to mirror, which are these 4 circles, and voila, I have all my screws, hopefully. And it's gonna ask me if that's the direction I want, which is not, as you can see. I want this direction. It's also gonna ask me how big this whole this screws should be, how the depth of them should be. And well, I said the diameter of the bone is 35 millimeters, outer diameter, plus the 4 millimeters of the implant, that's 39 millimeters, plus the 1 millimeter of these offsets from the screws from the top of the implant plate. So that should be 40 millimeters. Let's see if I got that right. Well, we can't check it here, but if we now go to the assembly, you can always toggle there or also here. You can go from part to assembly. And as you can very nicely see now, well, not like that. I really hate this perspective view. As you can nicely see there, it's down to the X. Yeah, the screw is through the whole bone. Okay, nice. This looks great, but most of the work still has to be done. First, I want to check that these section assignments were not destroyed by, as you can see, it's all still selected. So the section, yeah, it's the whole thing, because it's one part. So, but when you make different parts and you start changing things, maybe the section that you assign the material as part you assign a section to is different. Anyway, let's go on the bone as well to check that quickly. And of course, well, here we just made some holes, so clearly it won't change. So the next step, you can do this in all kinds of different orders, right? But okay, what I like to do is now go back to the assembly, and okay, this part, this is when things start getting a bit tricky. So we have to mesh this, right? So if I were to go, I'm gonna illustrate what the problem here is. So you go on here, you go on the mesh section, and let's say you were to see, first it says dependent part instances cannot be edited or assigned mesh attributes. Okay, so what I found is, yes, I mean, you don't have to do this, you can mesh it with dependent mesh, but I like to make them both independent. such that I can make all kinds of changes directly in here. Right now it's all orange. Orange in Abaqus is basically saying you cannot, in the mesh section, is you cannot mesh model. You cannot mesh it. It's not going to work. If you see, if I say, oh, mesh instance and mesh post instance, is going to say the selected regions cannot be meshed automatically using the assigned element shapes. So you could go in controls, select the section, the instances to be assigned controls. You could go in tetrahedral, and now it's actually possible to mesh them, right? I mean, I think so anyway. I think if I assign this at that, takes a while, but I hope this doesn't crash. Okay, so you could do that, right? She's fine, right? But as you can see, I mean, for the contact, first of all, it's they're all a little bit different, all the elements. I don't think it's very clean. And the most important part is that for the contact, so the plate and the bone, for instance, I can make this transparent to see also the one of the screw. Let's not make it transparent. You can see also here, they don't really fit together, right? So it would be nice if the nodes of one part fit with the nodes of the other part. And in general, I believe the hexagonal elements are much nicer to work with. This is something that probably an expert in finite element would really understand more about. And you can go into the Abaqus guide, which is extensive. You can find all kinds of things there. Unfortunately, not a lot in. Well, I don't find it that good, but it's very large. A lot of information. Okay, I'm gonna go back to my controls, and actually, I'm gonna go back to hexagonal, and it's gonna delete the meshes and tell me again with orange that I can't actually do this. But I've discovered that I can, right? Discovered that I can if I'm just a little bit smarter. I'm just wondering why that's. No, shouldn't be a problem. Maybe it could be a problem actually. Let me just go here, see why that is. I think it's not going to, yeah, I think this line isn't actually, no, it is going here. Yeah, it's fine. It's just an error of the assembly that it looks as if, like, anyway. So what I do is I make some partitions, right? And when you make partitions, sort of Abaqus sort of understands that different sections of the bone, according to what you partitioned, are to be meshed differently. I don't know how the algorithm exactly works, but I've come up with a way that you can partition these in such a way that it meshes well with hexagonal elements, so this sort of rectangular shaped elements. Okay. So when you create a partition, it gives you different options. I want to create a cell partition because if you want to cut parts, you really have to go with cell. Other things just for faces, so like surfaces or edges. Anyway, I gotta go with cell for this. So I want to use a datum plane, right? For this first part. Actually, in this first part, I could use. No, yeah, I want to use a datum plane. So first, I want to create a datum plane, right? And I'm going to say create datum plane offset from plane. Or you can offset also, I think, from normal datum plane line and point. I'm gonna go with that for now. So you can do this one, and then this point, and the datum plane could not be created since the select point lies on the intersect. Actually, okay. Like the point not lying on the intersect. Okay, fine. Then. So I go with this one, and I think that should work. As you see now, it created this plane like this. And I want to make a cut there such that you can have a similar node between this and this bone and the implant. I'm a little bit troubled by this. So see if they weren't really matching. I don't particularly like that. Anyway. Okay, now to create another one, I'm gonna go back here as well and do the same for this one. Okay. Okay, next. And you're gonna have to trust me on this because I did a lot of trial and error. Next, you also want to do another plane that is offset from the YZ plane, and YZ 0, so it's just actually the YZ plane. Another offset from the YZ of 3. This is because the screws are 2.5 millimeters in radius, so 3 is a 0.5 farther. And doing these sort of like, I'm gonna enclose the screws in a little square, and you'll see later that in the mesh, this looks quite nice. It produces a nice mesh. So again, in the YZ plane, but this time -3, and you get another one here. Okay, so the other thing I want to do, I'm gonna go on the side here, and in order to enclose those screws, like I said, and also cut them in halves, because then they're like in 4 sections, the screws, and well, that just produces a nicer mesh. So I'm gonna start with, if I do another plane in the X, offset from the XY to 75, actually, it's all going from here. This is the actual axis, so 75 would be here. But I want to start with this side. So that would be 225. You can see it's nicely here exactly. So it's gonna also create a nice nodes, all the nodes there on the same place for the implant and the bone. Another one at 75, and then that's the other one here as well. Then I'm gonna make some more planes, but I'm gonna make them with reference to this one. So for example, this one, it's gonna be like that. You have to define whether you want that in direction or flipped. So flipped and 15, and that's directly in the middle of this screw. Then another one, flip 15, then another one, probably flipped. Oh no, I didn't flip. So 15, another one. I'm doing this like this because in 15 is, I'm constantly using 15, so it's easier. These kind of operations, I'm assuming there is a way to make them way faster. Also, you can use codes for, I think, I mean, you can do it from any program, but I think this works easier with, in combination with Python. A colleague of mine, postdoc that's helped supervising me on this thesis, he actually, that's what he does. He just uses scripts from Python, and that just, you can run this very much faster if you already have everything in the code. But it's nice to do it at first like this, because then you know what you're doing more precisely. Okay, so next I'm gonna actually make another one that's 15. No, that was wrong. So if you want to delete things, you go here in the features section, and I don't want that last one because that last one is a repeated plane. You want to keep this as clean as possible, by the way, because if you start doing all kinds of things, and later it might interfere interfere with each other. It's a plane or a cut that you make. Okay, I want to make another plane that is from here, but it's only 3, such that it is a little bit offset from the end of the screw, as you can see there now. Another one with this one of -3, and then this one again 3, again, -3, this one 3, this one again -3, and this one 3, this one again, and so on. Actually, I don't know why I made this one in the middle, because later on when you have a fracture, you're gonna want to use a plane in the middle to cut it and make similar things to the fracture model, which in my thesis is one of the models. In most cases, is the only model actually. Again, this is a really annoying part. If you develop the script to do this, or just any way that Abaqus can repeat this without me having to click and click, I'll be very grateful if you can share that with me. Okay, now that that's done, I tried a lot of things before. This is so far what works best. Okay, so now I want to make the partitions. So you say use datum plane. For the first one, if you do this, by the way, it selects everything. Okay, well, this one has to, because it's only one part. You'll see later what I mean. Right. So select the cells to partition, and I selected that. Select the datum plane, and then that one. So it cuts through that with that plane, right? Now select the cells to partition again for the next cut. I select these two, and then I enter, and then partition definition complete. Yes, so I create the partition, right? And now it's partitioned like this quite nicely, so that it fits well with the implant. And I have this one, which is a little bit less intuitive. The reason why I select everything, by the way, sometimes when I'm making a cut that doesn't really matter what I select everything, then I just select everything. Make sure everything's like that I need is selected. So I go again. The reason why I'm doing this is trial and error. I've tried other things and it didn't work as well as this, so I'm doing this. So again, every time I just select the cells, enter, and then you click the plane that you want to use, and then you enter. And this is a bit of a boring, really boring procedure, because it's time consuming. It would be very pleasant if this was automated. But I'm about to be finishing my thesis, so I'm not gonna go into making a script out of this. Just perhaps the best way to make it automated. Okay, so I'm sectioning, partitioning all the area around the screws. Maybe right now you're thinking, why is he doing this? What's the point of this? Well, you'll see later. Or perhaps you're at a point you've tried a lot of things and you understand that Abaqus just needs these for the meshing part. So again, you see all the green parts are parts that I can mesh now, but the orange parts are parts that I cannot mesh. So another technique I found useful for making sure I can mesh these cylinders here, well, this orange part, is using these extrude sweep edges. So what I do is I first selected the cells to partition. Again, I press enter. Then it's to select one or more edges to sweep. And now I want to sweep these edges of this circle. And now you say I extrude along direction. And I go and I want this direction, but flipped. So I want to extrude these edges all the way down such that it cuts through the cylinder and it separates the cylinder from the other edges, and that just helps. It just helps to define the Abaqus what I wanted to mesh, right? How I wanted to mesh it. Actually, I don't know exactly how Abaqus interprets this, but I'm assuming that's what it does. Okay, so I go and I did that, and let's see what happened. Yeah, you see. Ooh, wait, actually, that's not what I was expecting. I'm gonna go and repeat that step. Maybe in all the talking, you see here, it didn't select this one. I'm gonna go and delete that and repeat that step. So I'm pretty sure I know why that happened. See, this is the reason why at the very beginning, when I made these holes, I was making sure these sketches, and I was making sure that that when I made the circles, they had these little things in the side. Is exactly because of this. Well, now they're on the top, so maybe it's fine if they're in the top. Basically, I don't know exactly why this matters, but it does. Abaqus interprets it. Do I need it to interpret it when I do this? Let's see if for the bone I also did that with everything. I think I did, but let's see. No, I didn't. But it's nice that I make mistakes, because then, you know, if then you learn more, right? The person watching this video. If I didn't make the mistakes, you will know what the correct way for doing these is if you run into troubles. And I hope that was a good excuse for my mistakes. Okay, so I'm gonna go back to my assembly. Hopefully it didn't. Sometimes when you change even the minor, even really minor things, it goes and says, you know what, the partitions you made before are not valid anymore. So you gotta go and repeat the process. And by the looks of it, it's taking so long. I think that's what's gonna happen. No, I didn't. So all the cuts I did are still there. I think so anyway. Yeah, they're still there. You can see this black line only appears when there's a cut. Otherwise, there's just the yellow lines. Okay, so I think now this should work fine. I go on partition. I'm gonna select you again, and these are the edges I want to use for partitioning. You can see now that it's selected the whole edge, because I don't know, like it's sort of like if I put that point in the sketch somewhere here, then interprets this as two different edges, and that messes things up. It's not symmetric anymore, and yeah. When I go again, I select these are the directions for the sweep of that partition. Okay, so you see, oh my god, what now? Delete that again. I do apologize for this. I have another model where I just constantly do this because all the sketching was already done. I hadn't worked with the sketching for a while, so anyway, let's stop making excuses and actually do this. So again, I got tools, partition, extrude, sweep, and my edges, and this should work, right? I mean, what is happening here? You can see here, there's a little bit of a mistake there, huh? Even though I thought I put it where it had to be, it seems I didn't. That's this one actually. You can see, it's actually supposed to be there now. Let's see if I can do this through fixing this. So I say coincident U and U. You see that's very nice. Because then now I'm gonna move U again, and I'm gonna say I want you to be coincident with these. You too. And I'm gonna say I want you to be coincident with these. I think that's what I did before, and this time I just I forgot to do it because I haven't worked with these sketching tools for a while. Okay, but now, and I don't do it for the other side because it's the mirror of these, right? You can see this is why I'm doing this video, because if there's somebody working with this later on, I don't want them to spend as much time as I did on these technicalities. Okay, again, I'm gonna go and say coincident U, okay, coincident U, coincident U, okay. Coincident U. All right. And now that should work fine. I hope I didn't forget to regenerate the other one. I did, but still do it now. Okay, so I go back to my assembly. It's gonna take a while again, trying to recalculate everything, because every time you make a change, it tries to recalculate everything, see if it has to change something. And I think we should put some music because it's getting boring. I go back to my mesh model, and let's try this one more time. Now this is very much perfect. I think so. Bonito. Todo me parece bonito. Yeah, I've added some singing to this exciting video. Okay, so I keep doing that for each screw. Okay. And you keep repeating this. This is really good for developing very robotic skills. You just have to do the same thing over and over again. Some call it monotonous. I would say it's good therapy for developing patience skills. Cuando te va bonito, bonito que te va, cuando te va bonito. Okay. Let's do this for this one too. Qué bonito. So when you don't see me clicking on these things, here's because I'm pressing enter, right? And then I'm also pressing shift whenever I want to select multiple things, by the way. You cannot forget that. Select any edge for the direction, by the way. It just has to be vertical. And then make sure the direction is the correct one. Okay, now I also want to make sure that this line here with this line is the same for the screw and for the bone. So select the cells to partition. So I selected them. No, I didn't. Wait, anyway, select the cells to partition, and I select only the screws now because, and when you do that, it selects everything. By the way, it's very nice. If you only click on one, then it doesn't. It only selects the closest to the screen. Well, you know what I mean. But if you do these like these, then it selects everything. That's very handy. Okay, so yeah, that's the cells I want. And I'm gonna use these two edges to sweep through. And for direction, I'm gonna use the actual axis itself. And I'm gonna create that partition. And what that's gonna do, hopefully, first, yeah, exactly. So it created a partition here, and now the screw is hopefully gonna be in the same place with these, right? So I do these now. And also for this one. And now the mesh hopefully will be exactly the same for the screw and for the bone. And that's very handy for when you define the contact, right? And this direction again the same in this bottom part, right? I mean, I think you sort of understand what I'm trying to do, right? Ooh, yeah, okay. This might not work other time. Oh, it did work. Okay. So now it's I mean, if I just to show you what I did. Here you can always go to this part, create display group, and you can show your. So I wanna get rid of the bone for a second here. So you just go and remove, and you can see that what I did is basically I made a partition here on the screw, only the screw, and also a partition here. You can't see that one, but it is there. There's a partition here for. You can see it better here, maybe. Let's see. See, this is so that it follows exactly the bone. And the mesh is going to recognize that from the meshing tool of Abaqus. Okay, so wait, what am I doing? So I'm gonna bring back my bone. You go and add. Okay. Okay, the final part now is I'm gonna first delete whatever. No, there's nothing to delete. I want to seed these So you can, with this seeding tool, you can tell it how many of these points you want it to have, so many nodes per certain areas, right? Certain edges. So I want these edges, which is actually selecting all of the ones along the length, along the depth, and these edges. And this is something you can only do in these independent parts. So you go on done, and it gives you two different options. You can either do this by size. So in that case, it makes it plays with the distance between the different edges. So it's basically the size of the element. It says approximate element size, but I want the number. So a number of elements. Basically, I'm gonna say how many elements I want per each of these edges. And the nice thing about that is if you do this the same, I'm gonna set it at 4, for example, and apply. So you can see here, it gives you a preview. It's the same exact thing for the bone and for the implant. And with size, you cannot do that. So you should do it by number when you're dealing with these concentric and circular surfaces. This is nice. And you can also do bias things. It puts more mesh on this side and on this side. But for now, I'm not gonna use that. So that's great. And now, finally, I'm going to mesh these instances, and it takes a bit of time. But as you will see, it looks quite good. Well, screws, the number of elements could be improved, but actually, I want these to be the same number of elements as these, so there's a bit of a problem there. But it's quite nice. I mean, you can already see it's very nice, right? Look at these, this is beautiful now. And even here, so it's quite good, right? It's very good. And if I make these, I think I might be able to make this transparent. You can also see, well, it looks as if it wasn't the same, but this is a circle, right? So it pairs up with the part of the bone quite nicely. Anyway, hopefully you can kind of see that. If you're doing it as well, then you'll see it even better. Now I'm going to do this. I'm going to seed the instances actually, because I want to make sure that this is, so I'm going to first make it 3. Yeah, it's going to delete the mesh. I want these to be the same for each of them. And that is not what is happening right now. I'm not very happy with that. Let's see if that decides to work now. Aha. now you can see this is perfect, right? I mean, it matches perfectly. These are hexagonal elements and they match really well with each other. You can use the tool I showed you about meshing more here, or you can also divide this edges into different ones to mesh it differently. It's a bit different. It's not fully symmetric, so you can also change that a little bit if you want by in number of elements in each sort of edge to be the same. But it's not really that important because I'm mostly interested in the contacts here. So okay, so this is for me anyway, the process that people might struggle with the most. The next process that might be a bit tricky or at least time consuming if you're first doing it and you don't know about this handy tool is the interactions. So it turns out most people are just gonna go here. They're gonna be like, okay, general contact, and then they go and define things. But I would say go cancel there. Do not do that. Go on this beautiful tool here. It says find contact pairs. You can set the tolerance for the separation of the contacts you are looking for. It's usually the right one, I guess, at least for me it is. And where do you want it to search? It tells in the whole domain. So it's gonna search for all the contacts. And it does this really well. You just click find contact person and look what happens. Okay, so it takes a little bit of time, but definitely less time than you would making all these contacts yourself. So this is the contact. You can see it highlights here. The red one is the master surface. The purple is the slave surface. And these are all the contacts for the screw and the bone, which is nice. That would take a lot of time. What I do is I select them all, right click, and I merge them. So you only have the contact now between the screws and the bone, and between the plate and the bone. Then you say OK for contact interactions. Right, so I forgot a little step that I'm gonna have to do here. So you actually need an interaction properties. I'm gonna call this friction. I'm gonna call it frictionless or friction 0, 2. And then you have to define, so I can define it as tangential behavior. You can define it frictionless, which is what I was going to do before, and that's why I was going to call it frictionless. But you can also define it with a penalty, and you go here and you get the friction coefficient that you want between those surfaces at 0.2. There's more other options. There's tons of options in Abaqus, a lot of options. You can find out about them in the Abaqus guide. I don't know all of them, right? So I'm not really that much of an expert in Abaqus. I'm just doing my master thesis on this. Anyway, so you do that, and now you have these two contacts. Nice, and you can right click, set edit, and you can change this finite sliding or small sliding. That's to do with how the nodes move relative to each other during the simulation. Small sliding is usually faster, and as explained in the Abaqus guide, it doesn't lead to too many inaccuracies. Also, well, normally node to surface would be quicker as well, but here it doesn't really matter too much for me because, as you saw, basically what surface to surface means is that it grabs nodes, not the nodes, but points in between nodes that are closest to the nodes of the master surface. So in the slave surface, it grabs points in between nodes that are closest to the node in the master surface, and it ties those or whatever, it makes those interact with each other. In the node to surface, it just grabs both of the nodes from each of the master and slave surfaces. But for mine, it doesn't matter too much because the mesh is so exact. That's why it's nice to have such a nice mesh. It was time consuming, but it really helps in making sure your simulations are better. Okay, so I'm gonna use small sliding for both of them. Small sliding. Okay. So there's a, yeah, I mean, oh, I forgot to define that there is actually one gap between these two. Well, normally in real life, there is a gap between the plate and the bone. Well, I'm not gonna do it for now, but just so you know, for future reference, there is a gap between them. And next thing you can set is, well, first off, you have to do field output request. Now I have to create a step. So this was the initial step. Now you create a step, and I'm gonna do the static step. It's a static analysis. It's not dynamic. It's just I'm just looking at the results in a static mode, right? Anyway, you can explore those options more. For my project, that wasn't so important. And then you can change the output of those steps. So by default, it takes the stresses, which is what I want. This is a stress component, so the 6 in 6 directions, 3 normal and 3 shear directions. And the strains, it takes a lot of strains. Sorry for the language, but I just actually want the total strain components, which is again the 3 normal and 3 shear. And displacement, also just the translations and rotations. In forces or reactions, it takes a lot of different things, and I don't want all that. So I'm gonna click that. It's faster the less outputs you wanna give it. And these, I want C-stress, which is the contact stresses. So I said that as well. And I wanted to do in the whole model. You can set other things. You can set like for just 1 point. You just want the results for 1 point, and it's even faster, right? Okay, and they have their own variable names here, which is how you would recognize them in the scripts of Abaqus. Okay, so that now I've defined what the output should be. Basically, everything should be now. No. Of course, I need to apply some loading, otherwise nothing's happening. Some loading to these, and normally also some boundary conditions. But to apply this loading, I do the following. So this part is also tricky if you haven't never done it before. You have to, I want to create a moment. Let me first explain what I want to do. I want to create a moment around this, like, so that the bone is in pure bending. And for that, I want to bend this like this and bend this like this about a point here and about a point here. So actually about the x-axis, right? Moment about the x-axis in this point, but no, not here, but here and here, right? Okay, so for doing that, you have to define a point here, which is actually here, a point here, and for that, make a reference point. And okay, so it already made it there, as you can see now it's there. And I want another one to be here. Let's see if that made 2 in different locations. Yeah, so it's one here and one here. Okay, it's perfect. Now I'm gonna create a constraint. What I need to do to apply moment to the whole bone and not just that point, I need to tie that point to the surface, and you can do this with coupling. And select the constraint control point. So I'm going to select that reference point. Bigger selection. Okay. Yeah, so that's the select the constraint control points, done. And now it wants the surface. So for the coupling is between this point, this node, and the surface. The surface, I want it to be all of these surfaces. So I select all of them, right? I want it to be a kinematic coupling, but this part is essential for the best results. You just want to tie them around U3, which is the Z direction, such that they have the same displacement in the Z direction and around the x-axis, because the node is being the moments are being applied around the x-axis, right? This axis here, so it's coming outside of the, yeah, I described it earlier, around the x-axis in this sort of in this plane, the plane of this surface. So you do that, and then you do the same for this one. For another coupling, constraint to, well, name it nicely, but then you say surface. You can also define a region of nodes, eh? But anyway, for now I'm going to say it like this. I think I did it different because I don't want these surfaces to later affect things. But oh well. This should work as well. And there's other things you can change. I've played with that before. You can try it just to see what it does. Now you can read about it in the Abaqus guide. Anyway, for now, this works well. Again, this is very important. Leads to the best results. Otherwise, I think it just kind of assumes that they are tied in other directions too, and it gives the wrong output result. It doesn't give a constant stress throughout the whole length of the bone when you just ran it without the implant, and it should be constant because you have the same moment at every point. This is pure bending. It's the same moment at every point of the bone, which is about the x-axis. All here have the same, so at the same distance from the same radial position, it's the same moment, right? But when you have the plate, of course, things change. And then the stress changes as well. Okay, and now we can define our loads as moments. So first, load 1, moment 1. Let's go on. Asks me for the point for the load. I'm gonna go and I tell it this one. And I'm gonna around 1. CM1 is around the x-axis, and we still want that one. It would be 60,000 Newton meters. So what's that? There is a reason why I'm doing that 60,000. I'm not gonna. It's something to do with that. I'm assuming that the weight of a patient is what is it? Weight of a patient is I think it was 60 kilograms. In which case, well, if we take gravity as 10 newtons per kilogram, it's 600 newtons acting downwards. Well, acting in these, acting like these downwards, right? And in which case, it would generate the moment. So if you say a force here of 600 newtons, then you times that by the radius is about it's more, but let's say it was 10 millimeters, then that's 0.001 0.01 meters, and if you times that by the 600, you actually end up with like 6 Newton meters. But then I'm making these in times 1,000. Okay, so you just have to trust me on that one. I did all the math. You can look at my paper, which my master thesis, for the explanation, better explanation than this one. But it's something around the lines of what I just said. Okay, so the second one is going to be M2 another moment, and around this one also here it's uniform and it's 60,000. Oh wait, no. If I do that, they both go around these like in the clockwise direction. So if I do it like that, it's just going to done. No, I want to see if you look at it like this. Basically, I want this one in the clockwise direction. This one should be in the anti-clockwise direction. So I'm going to change this one to be negative. Oh, well, yeah, now that's now it appears that actually the anti-clockwise direction is the positive one. So I gotta go with this one, negative. Yeah. Okay, so I think we're ready now. I mean, normally you would want to add some boundary conditions, but you don't need for this. It's just pure bending, so it's gonna move. It should just have a constant moment all throughout. Okay. So I've defined most things, right? I mean, you can just create the job. Which you're gonna call no fractor. Well, you can normally just say data check, but I'm gonna go straight to submit because I'm a little bit impatient. This has been quite a long road. Sometimes it doesn't work, and I have to find out why. But here I set up a contact for both the plate and the screws. For it to go faster, you can set up a contact only with the screws. But the results are a little bit more appropriate when you do it like this. So that's submitted. You can actually go here and monitor to find out what it's doing, and if there's some warnings, then it'll give them to you here. And there are some warnings, and it'll tell you in error translation. Well, you can read that and change them whenever you want, but I'm not going to. I'm just gonna wait a bit. Also, as you might have learned previously, generally the less number of elements you have, so the less denser the mesh, the less dense the mesh is, the faster your simulation would be, because there are less equations, basically, right? Less equations to be solved. So for faster calculations, just reduce the number of mesh, but the higher the number of mesh, the closer the system is to a continuous system. And in reality, you're trying to simulate that the real system is actually continuous, and so we're trying to simulate that. So you can see here that it solved the problem because it has friction. I added a friction coefficient of 0.2. Then it's nonlinear, and it solved the problem in 10 iterations. And I go into my results, and I go on deform shape first, and you can see that's quite. I mean, it's what you expect to happen. You can run a little video as well. That's what you expect to happen, right? And if you take off, you can go here and take off the implant. And you can run a little thing as well. And you can then go here and go here. Let's look at the undeformed shape. And that's nice. So you see there's there's more stress on the ends. And you can see that here because so red is higher stress. But a better way to see these, and this is something my professor taught me. First, I thought this is great. I mean, it's beautiful to see these. You can see every point is very informative for relative things, but it doesn't really tell you. If you want to be exact, it's better to go with a linear, like a 2D plot. This is a 3D, right, surface. So to do that, what you do is you create a path. You can name it, but for now, I'm not going to bother with that. And then I'm going to create it at the top part of the bone. You can say, okay. And what that did basically, then I go here and XY dot to create a plot, create XY dot to basically create a plot from the path. And it's the only path I have is that one. So you can see the path goes along the whole top surface. And you want to include the intersections. I want to do it from the undeformed shape. If you do it from the deformed shape, a different result comes because it takes the points from the deformed shape. You can change the field output to plot whatever you want. For now, I'm going to put this from meso stress. Also in the stress within each variable. For example, see, well, yeah, so stress components. So you can plot the von Mises, but you can also plot each of them, and then you can. I'm gonna go for von Mises stress, and you plot, and this is what comes up, and this is much nicer. By the way, you can always click these to recenter it, because you can see that. Yeah, we saw before there was some red there, but you know it's high. But here you can see much better what it actually is, and this is what I work with in most of my thesis. I want to try, and there's the stress peaks at the edges of the plate in the bone, and I want to try and reduce those, minimize those stress peaks by changing the material properties of the plate. All right. Okay, so I've now showed you how to do that. I might upload some other videos to show how I actually optimize the material of this implant in different sections. So I make a functionally graded plate by modifying the material at different sections, and that effectively reduces these peaks that you saw before. But there are some other restrictions. You want the bone to heal properly, and yeah, for details about that, you're welcome to look at my master thesis. Hope this was helpful. Let me think if there's anything else I want to show you for now. No. So goodbye.